Okay, so hi everyone. My name is Artem, and today we are going to have a JAX tutorial, which will give you introduction to JAX. And basically, the reason we are giving this tutorial is that homeworks 3 and 4, the last two homeworks, one is about DQ and another about policy gradients, they will be in JAX. And so basically, JAX is a modern and popular deep learning framework, but it not only allows you to work with neural networks, it allows you to do many other things, and it is particularly popular in the reinforcement learning community. JAX was initially created by Google, and Google uses it in all of their experiments, including the biggest large language models, such as Gemini. As well as JAX is used by people who don't have access to big resources to just do stuff in Colab, and this allows people to do very efficient. So what we are going to start with, we are going to just import JAX, and as you can see, JAX is just an importable library. It's a Python library. So I shared a Colab link to Piazza. So you can go to Colab and try to open this link in Colab and see if this line works for you. Just in Colab, it should be working without any installation and all of this stuff, because in Colab things are already pre-installed. So today I'll cover two things. Hopefully, the first is what is JAX, and so that you understand what's the key principle behind it, and how to things JAX way, and how to write code, such as it runs very fast in JAX, and then we'll see how to do that things in practice. I'll start with a philosophy of JAX. By the way, when I okay, uh, when I talk, I won't look into the chat. So if you have questions, just don't hesitate to interrupt me and ask your questions. And this is mostly concerns people who are online. And I see that there's a question in class. No? Okay. So I'll start with the question: what is a good framework for machine learning? And the answer is simply it's the one that you already know, that you don't need to learn anything to work with. So the philosophy behind JAX is that we need to build on top of as few things as possible. And in particular, JAX builds on top of two things. First is NumPy in Python, and you're supposed to know NumPy already because this is like prerequisite of the course. So this means that you already know some fraction of JAX, and just plain math, because JAX, as you will see, it's very mathematical. It's very understandable in a mathematical way, because of certain design decisions behind JAX. So when we run NumPy code, the first line we start with is just import NumPy as NP. And so JAX is uh, changing this in a straightforward way. It just has a subpackage called jax.numpy, and we can import it. We could import it as NP, but we imported like the best practice. Current best practice is to import it as JNP, and all the implementations are written like that. And so in theory, you can take uh, this. There are some uh, caveats, however, but in theory, you can take almost any Python code and just change import numpy SNP to import JAX numpy SNP, and in theory, it might work. But as we will see, it's not always the case, and there are some corner cases you should think about. So yeah, that's it for today. Thank you very much for your attention. Yeah, but of course it's a joke, and but this joke is just for you to see that JAX is like built on top of very known things and very widely usable things. So just as a first example, what we can do matrix multiplication, and here it works exactly the same as in NumPy. I create two matrices. One is 2 by 8k, and another is 8k by 4, and then I just multiply them. These matrices are ones, and actually, as you can see, the answer is correct. The result is matrix 2 by 4, and all the values are 8. And then what you can ask, like, where this code is running, like when I compute matrix multiplication, where it's running. And by default it's running, JAX is selecting the best device that you have. If your system has GPU, it will run code on GPU by default. So the code that I just run here, it is literally executed on GPU, because I'm running this in the environment with a GPU. And if you don't have GPU, it will show CPU here. If you have TPU, so for example, Google infrastructure environment, if you go to Google Cloud, if you rent resources there, they will have TPUs. But even before this, let's see actually what happens in Google Colab, what like this line outputs us. And this is like the only and the first time I switch between tabs. And this is just to show you how to work with collabs, because collabs are very useful tools for like playing with JAX code and so on. So I'll start with pressing connect, and JAX is Google is supposed to allocate me runtime. Runtime basically means it's a computer. So as you can see, right now I connect to CPU-based runtime. I'm going to import JAX. So as you can see, it just runs and I don't need to do anything. And if I do JAX devices, and by the way, I don't have Colab Pro. This is just basic free Colab. It shows me CPU. However, I can switch runtime. I go here, I press change runtime type, and I switch to T4. T4 is a GPU. So I need to reconnect to runtime because it's a new computer that I connect to. And I again do the same thing. And this line now shows me that I have CUDA device. And finally, I can connect to TPU. And again, this is something that anyone in the world can do for free. You don't need like to pay for that, obviously. But unfortunately, TPUs are not that much available, and they are available for like 3 hours of continuous usage. So if I run it like this, I'll see several TPU devices. Yeah, so it has 8 TPU devices. So yes, another thing that we can do in JAX is differentiation, and this is really where the magic of JAX starts. So suppose that we have this function that I define here. I define f of x that returns me x times 2 when x is positive and x squared when x is negative. And JAX has a function called grad that computes the gradient of a function. So let's run this cell and see what's the value of 3 and what's the gradient of 3. So as you can see, this is correct computation. The value of 3, the value of f at 3 is 6 because it's just 3 times 2 and 3 is positive. And the gradient is what? Is for a positive x is just 2. So it returns me the correct gradient. I can even call the gradient of the gradient, which will give me the second order derivative. And this is, guess what I should expect and where should I get? Who can guess? Yes, it's 0, exactly. Yeah, but I'll restore to the original state. Yes, so but the first order gradient is 2. So we can also consider like negative case for you to see that it really does its job. And when x is negative, we just return the squared value of x, and the gradient is different also. It's not 2, it's 2 times x, where x is negative, so it's minus 6. And again, if we compute the second order gradient of this, it is what? Yes, exactly. And the third order gradient is exactly. So yeah, JAX can differentiate, can compute arbitrary number of derivatives of any function. So what did we just do? Basically, we created a derivative function as a function. Yes, there's a question.
Okay.
Hello? Okay. So basically, we just created a derivative function, and this is another function. So we have function f, and gradient of f is another function. It has some inputs and it has some outputs. And mathematically, it looks like this. So when I consider nabla f is not just a vector or something. This is another function that has certain inputs and certain outputs. And so this is how we should use and think about JAX. So JAX can, in theory, differentiate any computation. However, like you can think that there is stuff that I can do like completely. It's a completely different stuff than like plain computation, such as if I go to internet, or if I call ChatGPT, or if I don't know read from keyboard of the user, like what happens in that case. So unfortunately, um, not all the computations are actually like properly executable by JAX. Not all the computations are friendly to JAX. And so when we are working with JAX, so the first thing you should keep in mind, you cannot write like arbitrary code. You should write certain types of certain like style of code such that it is friendly to JAX. And I'm going to explain like how to do this. So in general, how can we tell that the computation is differentiable? And so there is a whole programming paradigm that actually answer these questions. And this paradigm is called functional programming. And if you go to any tutorial about JAX, you'll see that in the first like paragraph when people explain what is JAX, they say, okay, JAX is a functional framework that implements like functional paradigm, and we should write functional styles. So what does it mean for us? Uh, Generally, functional program is kind of brutal and hard, and we don't need to care about it that much. We only need to keep in mind two things from the functional paradigm when we write Python functions. So all the functions are so-called pure, so which means that they don't have side effects. Uh, Examples of side effects are I go to internet, I call ChatGPT, I read some input from the user, and based on that I compute the value and so on. So you can think of it this way. If I have sine of 0, I can just substitute it with the result of this sine of 0. So the function should be entirely determined by its inputs, right? So uh, is this clear? Because this is a central concept. Okay, so the hope is that this is clear. So this is the first concept. And the second concept is that there are certain functions, and we've seen already one of them. It is JAX-GRAD, that they don't just map numbers to numbers, but they map functions to other functions. And these functions, these are so-called higher order functions. They're in JAX, they're called function transformations. And so in this tutorial, we will consider a lot of different function transformations, and we'll see that they are actually very useful. And all of them are implemented by JAX, so you don't need to implement any function transformations. You need to only write concrete functions that work with numbers and then apply function transformations to them. For example, you write a function that computes this value, like that we considered in previous slide, and then you differentiate this function to like do some gradient-based optimization, for example. So these are two central concepts in JAX. And to see how exactly it works in practice, let's consider this scenario. Mm. Let's say I have a function that counts the number of invocations that I did, that I performed on this function. So I say that I have state, the variable state, which is initially 0. And when I call it, I just increase this state counter. And then I return whatever is dependent on state. So we see that two calls of these functions, they are not equivalent. The first call returns 2, and the second call returns 3. This means that this is not pure function. So pure functions that functions that are mathematical-like, they are called pure functions, functions that are only dependent on inputs to compute outputs. So this function is not pure because it changes the state of the outer world. So ideally, pure functions are such that every call of the function can be substituted with its result. So here it's not the case because two calls are not, it's not possible to do such kind of things. So let's go down. And in contrast to that, we can consider pure functions. For example, this function is pure, pure in mathematical sense because it's entirely dependent on input. So when we compute its output, it does not change by anything except the input. However, there's a trick. You can still depend on the outer world unless you don't change it, right? So in Python, it actually um, uh, very easy to tell. Like there's one way how you can very easily tell that you are breaking the purity of your function. Let's say I wanted to like update the state. So I write state equals to state plus one, right? And so if I run this function, it will get an error saying that state is not defined and I don't know where to get it. Yes, so because when I define it here, Python thinks that state should be local variable, and to like fix this issue, I need to define state as global variable. So when you do such kind of things, this should be automatically a red flag for you. You should never do this in JAX functions. You should always avoid these kind of things. However, you can depend on the outer state. So once the outer state is like is just used but not changed, this function will still be pure. Yes. So this is a little bit tricky, and so I I didn't add this part to the presentation because it's very technical. But technically speaking, in Python, if you dig into how into the details of like how Python works from the functional perspective, Python has I think which is called closure. So closure of a function is a set of all non-local variables that the function is using. And so basically, the reason, to be precise, the reason why both functions are actually pure is because their closures are pure functions. So even though this function worked with global state, if we consider the closure of a function, so by the definition of a closure is for a function f, it is another function such that for all the like global variables, it explicitly takes these global variables as input. So, and in your question, let me actually rewrite this function a little bit for you to see uh, how the situation will change. So I will rename it to uh, closure f, and I'll make it accepting state explicitly. So now, like, I consider the closure of the function f, and it just returns this. So in my case, uh, in the case that you suggest, the proper answer is that the first call will result in what we actually expect. So we'll add 0 to 1 and we'll have 1. And let's say we are changing the state of the outside world, but globally. So sure, we can just call this function another time, and this is just will be another call with different values. So oh, sorry, I should write closure, obviously. This will be just another call with just different values. So JAX actually is doing something like this behind the scenes when you do some function transformations. But keep in mind that you can obviously change the state, but uh, uh, your function will get like the up-to-date value in the closure, and this will happen kind of automatically. And there will be examples how actually this is happening in practice. And in practice, you almost it's not needed to like think about this, and it's not a problem in practice at all. So, um, okay, I think I need to zoom out a little bit. Yes. Yes, and uh, actually, I showed now I showed before what I was supposed to show now, but still. Okay, so let's consider these two functions. One is impure and another is pure. So impure functions, the first impure function, it counts how many times we call this impure f, and pure version of this function, it is essentially the version of the first one, but with a closure, with an explicit closure of state being passed as an input and then being returned as output. So, uh, so yeah. And so when we, let me define these functions. And then when we call this, we see that the initial state is 0 because we did not call these functions any times. And the first impure call return as this. So the state is 1 and the x is 0. And the new state, this in both cases, I just print the variable state. So when I access this variable, it changes in the second time compared to the first time. And this is because this function changed the state of the outer world. In contrast to this, when I, yes, so yeah, we'll need this example for later. And for now, let me consider these two types of transformations to see how and why things, to see why actually we need this purity of functions. So now we are going to consider the first two, like the second transformation. So the first one we already considered, it's differentiation to compute the gradient with respect to inputs. And this is the second transformation. It's called JIT. So JIT is generally a transformation to speed up function. So what the idea is that when you run sequence of operations in a function, when your function is like some computation, this is called computational graph. A graph where every node is some operation. So when you run some computation, um, what happens? Remember, I showed you in the beginning that when you do A dot B, you run it on GPU. But then you can do like plus C and then multiply it by D, whatever. And what actually happens is that I take A and B, JAX sees that we need to multiply them, it goes to GPU, it tells the GPU, please multiply me matrices, and then it takes this value back, goes to the next line, returns the value, goes to the next line, sees that, okay, we are going to add like vector scalar value to that. We are going to like go to GPU one more time and so on and so forth. So basically the problem is that there is a lot of back and forth steps between like Python code and the code that is run on GPU. And JIT is what gets rid of that. And we'll see that this can give like huge boosts. So on GPU, this can give like 5-10%, 5-10 times faster execution in some cases. Yeah, so in general, this is like compilation of the computation. So let's import these functions and see how purity of functions affect this transformation. So for you to know, these transformations, they assume pure computation, because the only way, essentially the only way to perform transformation of a computation is to assume that it's pure. Why? Because let's say it's changing the outer world. This means that there's some other computation happens in the outer world, and this means that we need to optimize that one too. So like it would be impossible to do. So instead of this, we kind of assume that it's not doing anything like this. So again, let's consider the same example. and let's see what happens if we try to compile pure and impure functions. So first, what I'm going to do, I'm going to compile an impure function. So remember that when I called this for the first time, I'm going to rerun it again. So my state is 1. My state is 0 here because I did not call the function. And now my state is 1 because I called the function once. And this function is pure because it changes the state of the outer world, being the variable of how many times I call the function. So I compile my impure function and I call it fast impure f. So before in the beginning, I print what's the state, how many times I called this function. And
Yeah, that's your
here
package.
I print not all the outputs
It'll
of this.
probably, he's probably going to come up with it in a second. No, no, I know, but just so that you have it that way.
So should I continue?
Right.
There's a question or there's a question.
Okay.
Guys, online team, can everybody please mute their mics? There's a couple of people with their mics turned on. We can hear your conversations.
Okay, I'll continue. So basically, we have state. Again, state is how many times we call the function. And this state should be 1 here. And then we call fast impure function and we return only the state part of it. So I remind you that this function, it returns 2 values. It returns the state and it returns like the whatever we want to output, like something state plus x or whatever. And so then we call it 2 times. So let's see what happens. First thing that you might notice is that there is certain lag. So we should have waited a little for a few seconds before this second row appeared. Second thing is that initially the state is 1 because before this line, we called this function only once. But on the first impure call, we return 2 because the first impure call, this call actually computes the result. But the problem is that the second one, it acts as if there was like two calls only. So basically, it does not change the state of the world anymore. So why this is happening? It's because JAX, by design, it assumes that you write pure functions, that you don't do bad job, and that you write functions that have only certain inputs plus potentially closure, and the only changes that function brings to the outer world is in its returned values. There is no outside world change within the computational graph. And essentially, in the first line, the reason why this line appeared a few moments after the first line, the reason for that is that compilation, it takes time. Even though this compilation is trivial, JAX is still performing some manipulation of code. It like translates this code into some lower level language, and eventually it reaches like the code understandable by the GPU, and this whole process takes time. But obviously, when we run stuff on GPU, GPU does not know that we need to update some variable that we defined in Python and Jupyter. GPU can only like receive values and then output values. And that's actually an example of why this purity is important, because when the function is pure, then we know that we can just take all things that this function receives, including stuff that is in the closure, send them to GPU or to TPU or to CPU or to like some other executor, and then just expect the returned value being like correct because the function is pure. So in other words, the fact that function is pure means that we can freely manipulate this function in any way we want, just to make sure that the results are always the same for same inputs. And this is actually what JAX is doing behind the scenes. So,
Please
and
repeat that JIT part again. What does that function do?
Can you repeat your question, please? Sorry, can you repeat your question, please?
That JIT function that you have written in the second line, JIT.
The JIT function or impure F function?
JIT function.
So JIT function, as you can find it here, actually, it's a transformation. It's a higher order function or function transformation in JAX, and it just compiles the computation. It compiles the computation to speed it up. So it takes F and it maps it to faster F that runs on GPU end to end. Okay. And the cost of this is that the state of the function is sorry, in this particular case, the state of impure function is being frozen at the compilation moment, and subsequent calls, they don't change the state anymore. And the proper way how to do manipulations with pure functions is this. So let's consider the case how JAX expects us to do these things. So what we are going to do, we are going to take this pure function. Just to remind you, let me again show you the definition. It just counts how many times we call the function f. So it receives state, it receives value, it increases the counter, it returns that counter, and it returns the value. It does not change the value in any way. So what I'm doing here is I'm compiling this function. I'm saying that now this function is going to be fast, and I create initial state is 0 because I didn't call this fast pure F thing. So my first thing that I'm doing is I'm calling fast pure F with initial state and some input, and it returns me an updated state. And then I take on the next call, on the subsequent call, I take this updated state and I use it as input state to my second call. So what is happening here, and the result is that I get some output results, but importantly, I get the second state being what we expect it to be. So first state is 1 because we call this function only once, and the second state is 2 because this is our second call. And so this is how you generally should perceive all JAX computation. It just runs some functions through the state that it carries over this computation. So you may ask, why do we need all of this difficulty? Can't I just run just okay, so my matrix multiplication, for example, it runs already in GPUs. So why can't I just write this code, assume it's on GPU, do whatever I want, matrix multiplications, and it will just work fast because it's on GPU. So let's consider an example where we get an actual speed up from JAX. So what is happening here? I compute the 1000th power of a matrix. So I take some A, which in my case will be matrix, and I just do a for loop of in total 1000 steps, because 0 steps I start with A. And I just do dot product between matrices with accumulated one and result. And then I return this accumulated. And this function is pure, obviously. So first, what I'm going to do, I'm going to just compute this function on an input to see how fast it runs. So this time it is like Python magic thing, which runs it several times and reports the average runtime. So as you can see here, it's finished in 33 milliseconds. Now I'm going to compile it and try to obtain the result. And you'll see there will be some surprise for you. So as you can see, it's very slow now for some reason. So I said, okay, so compilation will make stuff fast, but now it's slower. It's like, I don't know, 20 times slower or something. So it's now 2 seconds. It's very, very slow. Why is that? And the reason for this is that you when you transform a function with JIT to speed it up, you obtain a new function, and the first call of this new function will actually compile stuff. So surprisingly, when you say that my function is compiled through JIT, actual compilation is not happening here. Actual compilation is happening here and only in the first call of this function. Why? Because if I do, okay, so before I talk about this, let me execute the next line to show you that it's really got faster. So it took some time just because it ran several repeated iterations of the same operation, but the operation it's now running in less than 3 milliseconds, whereas uncompiled version was running in 30 milliseconds. So it became 10 times faster. And even remember that even here, every matrix multiplication is happening on GPU. But just because we are doing so many back and forth operations, we get a lot of drop in this performance. And so one important thing to keep in mind is that whenever you and actually if I comment out this and I run it one more time, you'll see that it's like fast. So some yeah, so it's as fast as the previous one. So however, let me call this function on another input. So again, I'm going to create another matrix which is a bit bigger, and I'm going to create results. So uncompiled run should be running just a little bit slower than this. So let's see. So it's running a little bit slower. And then we will run it on another input to see what happens. I will compile this to reuse the same compiled function, so I don't recreate this compiled function. So as you can see, and this is very important, another very important point about JAX is that we still spent reasonably big time to finish this execution. And the reason for that is that we actually recompiling the computation. Why it is happening is that we receive different values. We receive different types of values. Before that, we had matrices 5 by 5. Now we are having matrices 8 by 8. And so why JAX is doing this? Why can't it just compile it once and then reuse it for all the cases? It's because in general, so when we are talking about shapes and data types of arrays, different types, they in general assume different computations. That is why when we just change one shape just a little bit, in that case, you will trigger the recompilation of the entire computational graph. So, however, when you reuse, yes, so let's see that our recompiled function is indeed fast. So yes, so it is kind of fast. But the point of it is that once you compiled it, and once input data types and shapes are the same, it will use the same like compiled instance of a function. But when you once you send different shapes, different data types to your functions, this will trigger recompilation. And actually, internally, JAX holds this object called compiled power. It actually holds all versions of compiled functions, and when you call this function, with a certain inputs, it just infers data types of inputs. It sees, okay, which functions in my library I compiled, and then it selects a proper one. If it doesn't find the proper one, it just recompiles it. If it finds a proper one, it just runs it. And this is obviously happening very fast also. So there is a tricky part, however. Remember that I told you that functions cannot change the state of the outer world, right? So it's tricky how to do like array assignment, but because in general, array assignment can be thought of a change of in the outer world. And because of that, it might be not clear why, but the reason is a little bit low level, and it comes down to like CPUs and GPUs. And the reason for that is that there's no such things in mathematics. There's no such thing as array update. You can just create a new like matrix where like, so here I create matrix of zeros, and then um, all the rows, but the second and third column will have all ones. So in mathematics, I cannot define it like this. In mathematics, we write, okay, so A is a matrix 3 by 3 for indices, for like columns lower than 2 is 0 for regardless of what the row is. For columns greater or equal to 2, it is 1 regardless of what row it is. So when we and this can be dependent on some other like array, and because in general shouldn't be as simple as this. So my point is that since I said that JAX is trying to do some kind of pure mathematical computation, array assignments, they kind of break this rule. And so if I run this cell, it will show me an error. It will show that it does not support item assignment. And there is a way how to do. Oh, I think my presentation broke. Yeah, let me try to re-enter the presentation. I'll just do clicks. So instead of this, there is API that JAX provides. And what you do, you just do, there is so-called at notation. So you just use at field of the array, and then you select a slice to which you want to assign. And then you call dot set. There's also dot add, I think. Dot set, it sets the value to a given one. Dot add, it adds value as the name suggests, and so on. And so the thing is that just like it works in math, it creates completely new array. And this operation, if I again consider A is still a matrix of zeros. So, but here we create a new array. You may say that this is not very efficient, and when we have large arrays and we need to update it with little data, this will be wasteful kind of. But JAX is smart and it can optimize operation enough. And the fact that you are running pure operations in Python does not mean JAX has to do them on GPU. JAX can actually optimize them heavily to like reuse to like override some things when it thinks that needs to do that. And this actually is a concept that you are going to be asked to do in the homework. So please remember this idea. My slide switch still doesn't work. Okay. So the summary of what we just talked about. JAX lives in a functional paradigm, and it does so for mainly two reasons. First is to be able to compile functions into fast computation and then run into accelerators. And the second reason, which is kind of the more general version of the first reason is that we want to be able to transform functions into other functions. Example of such transformation is like JIT compilation, which makes the function faster. Another example of such compilation is JAX.gradient. And obviously you can compose this transformation, you can do gradient and then compile this gradient to get like fast gradient evaluation of a function. So in summary, if you open the website or the documentation of JAX, you'll see this image. And JAX essentially consists of three things. First is JIT compilation. Second is automatic differentiation. And third is XLA. So these are three things that JAX started with. And to the best of my understanding, this is what JAX abbreviation stands for. So we already considered these two. And the third one, I'll briefly mention what is this, but we are not going to talk about this a lot. XLA is that thing that runs behind the scenes to optimize your graph to lower it onto accelerator. So actually when you call JIT, you behind the scenes JAX performs XLA manipulation. XLA is another compiler that takes some internal JAX representation and maps it into programs that are digestible by GPUs or TPUs. Oh no. I need to. Oops. Okay, so that's the end of part one. What is JAX? Is there any questions? Or we can go to part two. Okay, let's go to part two. The part two is basically JAX in practice. So we'll use this concept to do some real stuff with JAX. And basically what we are going to do, we are going to build a neural network in the end. So before even talking about neural networks, one important principle that we should consider is random numbers generator. Because obviously, random number generation is something that heavily breaks the idea of pure functions, right? So, and this is a meme about this as an example. So someone tossed a fair dice and they got 4. So this is their like random number that is always returned from a function. This is a pure function. And so this is the only thing that JAX can do. So how to deal with that? And JAX deals with that quite gracefully. So it should not be surprising to you now that this is going on right now here. Essentially, what we just do here, we create special state array for random number generator. Essentially, if you're familiar with how random numbers are generated on computers, this is like the seed for pseudo-random generator. And so this actually allows us to view random numbers, pseudo-random number generation as deterministic process. It's deterministic process given the random state. So as you can see, we generated a random integer. As in that mean we generated 4. So let's do it one more time. We say we have the same key, take this JAX random key, and we generate another sample. Again, we got 4. I can do it many times. As you can see, we always get 4 because this computation is deterministic. And by the way, whole thing about JAX is that if you run this code on any device on any hardware where JAX is installed, you'll always get 4. Like you can run it on your laptop, you can run it on Colab. Just this code will always return 4 no matter what is the hardware. So this lets us view random number generated as pure functions. So so how this works in practice? To generate random numbers, we need to, as I said, we need to view the sampler as some deterministic function that works with the state. But since I show you when you reuse the same state twice, you'll get the same number. So how to get different samples? JAX has a solution for that. They have a function called split. So you call JAX random split, you pass in random state, and it splits this random state into two random states. And you can use your first random state for next computation, and you can use the second random state for actual random number generations at this step. So again, here I'm going to create a random key, the same as previous one. And you should already see the pattern here because since my function is pure, what I do, I have the state of the function. I have some input value. This is like the maximal value for a random integer to pick from. And it returns me an updated state, like the random number generation state, and sample. And so then I reuse this updated state for my subsequent call. And this, it gives me even another updated state. So as you can see here, we have different samples. But obviously these operations are again deterministic and we never get different values. And this is the way how we can define, how we can like do actual randomness in JAX. So, but if I change the random state, obviously the samples will be different. And so actually, if you look at what key is, it is just an array with some integer values. So this is the initial key, this is the key after the first operation, and this is the key after the second operation. They just changed in some way by JAX. So now it should be clear for you that a lot of computations, essentially all the computations that are performed by JAX can be seen as this pattern. We have previous state of the world or previous state of the things that we care about, that we need. Then we have input, we pass it to the computation F, and F outputs us new state of the world and the output. But this is actually, this pattern is used everywhere in JAX, as you will see in one of the next slides. So is there any questions about random numbers? Okay. And so now we got into the most cool application of JAX, the most powerful and nice function transformation that is implemented in JAX. It is called VMAP. So actually, in the beginning, VMAP was entirely the thing why JAX was created. So why VMAP? What it is doing? We can not formally define it as this. Let's say we have a function that, for example, maps R to R, but it can be anything. It can be mapping Rn to Rn, can be working with different things. And again, this is a mathematical function, meaning pure function. So VMAP is a function that maps Rn to Rn. And it is such that it is just applies, it now instead of scalars works with vectors, and it just applies function f element-wise to these vectors. So previously I had a function that takes scalars and outputs scalars. Now let's say VMAP f is a function that takes three-dimensional vectors and outputs three-dimensional vectors. So what it's going to do inside, it's going to take the first dimension of input, apply f to that, take the second dimension of input, apply f to that, take the third dimension of input, apply f to that, and then concatenate the results into a vector. But obviously, this is not a formal definition of VMAP. I don't think anyone can give it, at least in an understandable way. So, but keep in mind that it can transform any computation. And in case you're wondering what is n here, again, I already answered this question. Remember that when n is kind of the type of the input. And it's determined at like compilation time. So when we pass like 3D vector to vmap of f, it compiles into a function that works that work with like three-dimensional vectors. So it compiles into a function R3 to R3. When we pass like five-dimensional vector to vmap of f, it sees that, okay, I don't know how to work with five-dimensional vectors. I'm going to recompile, and it compiles into a function that works with five-dimensional vectors to five-dimensional vectors. Is this concept clear? It's also very important. It's also will be used in homework. Yes. Yes, essentially, basically the magic of this function is that it is roughly speaking equivalent to for loop. But it is doing this, as we will see later, it's doing it in a parallel fashion. So basically, for example, we'll have an example for this in a few slides, but what you can do, you can say, okay, I have a operation which is a dot product between matrix and column vector, and vmap essentially is a thing that allows me to convert this computation into a matrix-matrix product. Because if I consider my input to be like the vector and vmap only over this vector input, I'll add one dimension to vector. And essentially, matrix-matrix product can be seen as for loop over matrix vector products, right? So vmap will literally do that for you. It will do, if you specify it in a certain way, it will do it. We'll see this in the next slide. It will turn matrix vector multiplication into matrix-matrix multiplication, because vmap is equivalent to for loop, and matrix multiplication is equivalent to for loop over matrix vector multiplication. So in other words, it vectorizes the computation. It takes any computation. It can already be working over vectors, but vmap is making them working over vector of vectors if you pass vectors as input. So let's consider this example. We are doing inner product between two vectors. I have vector A, I have vector B, and I just compute their element-wise product, and then I sum them up. This is, by definition, inner product. Okay, so when I compute the result of it, it's easy to see that it's 3, because we compute just two three-dimensional vector of ones, inner product of them. But now let's see what vmap will do. By default, vmap considers all the inputs, and it adds one extra dimension to both of them. So initially our function works like this. It takes n-dimensional vector as one input, n-dimensional vector as one output, and it returns one-dimensional vector as a result. This is our definition of the inner product. And we apply vmap to this function, and now what just happened, we just added extra dimension to everything, to all the inputs and all the outputs. This is how it works by default. So now this is a function that works with n by m matrices. It receives one m by n matrix, another n by m matrix, and outputs the vector of size m. And this is, by the way, not a proper matrix vector product, because the result for this to be a proper matrix vector product, it should be like this. But this is just for you to see that there's a great flexibility in how you can do vmap. And in the next slide, we'll see how to do from this build a proper matrix multiplication. But yes, so if I run this code, I'll see that I just essentially instead of the unvmapped function would have worked with four-dimensional vectors of ones, and it would have returned 4. But we added one dimension to this computation, and now we can work with matrices. And essentially, we just repeated these vectors 3 times. So we have 3 times 4-dimensional vector and another 3 times 4-dimensional vector. And we map it to with our function transformed via VMAP. We map it to 3-dimensional vector with values of 4. Is this clear what just happened? Or I can go one more time. Okay, hopefully it is clear. So, but how to define like a proper matrix vector product? And here we can actually see how to do that. So we start with again with our definition of inner product of two vectors. We take a vector of size n, another vector of size n, and it maps these to one-dimensional vector. So now what we are going to do, we are going to define through VMAP, we are going to transform this computation into another one that performs a proper matrix vector multiplication. Why? Because we are only adding one dimension to the first input, and we say that it corresponds to 0 dimension of the first output. So 0 here we specify access for every input. We have 2 inputs A and B. Therefore, we have 2 elements here. For A, I say that I'm going to VMAP over 0 dimension, which means that I'm going to add extra dimension at 0th position. And as a result of this, I get here. I redefine my function as another one that works with not just vectors of size n, but matrices of size n, m by n. And n is the same as here. But B, since I don't specify dimension here, I say it's none. In this case, B is not V-mapped over any dimension. It's still like this function still expects that B is just a vector. And the result of this is a m-dimensional vector. And as you can see, this is a proper matrix vector multiplication now, because m for every like index in the m dimension, it's going to be inner product between this n-sized vector and this n-sized vector. That's why it's a proper matrix vector multiplication. And now we are going to just do VMAP one more time. So we are doing something analogous to previous operations. So now again, I say that my input access, I specify things for 2 of them. For the first input, which is matrix A, I say that I'm not going to VMAP. And for matrix B, I say that I'm going to VMAP over the first dimension, which means that, again, I add to the vector of size n, I add one dimension, and I add it at the position 1, which is like to the right of n. And if it was 0, it would have been here, if I specified 0 here. But since I specified 1, I added this to the first dimension of B. And also in the same way for the output, I say that I'm going to add this dimension to the output. And so now this function has a proper signature of a proper matrix multiplication. And we can do it in this way to get proper result of a matrix multiplication. So let's see what's the correct answer. It's the same. So, however, there is one important caveat here. Can we VMAP if? So if remember the very first function we considered, if x is positive, then we return x times 2. If x is negative, when we return x squared, right? The problem with if is that the computation is becoming dependent on input. When we vmap over some function, if imagine that we can vmap a function with if. What happens there? It means that now f, so our function f, it's supposed to work not just with scalars, but with vectors. And for some elements of these vectors, we will do one computation, and for some other elements of this vector, we'll do a completely different computation. And it's just our case that is simple, and we do like x times 2 or x squared. But in practice, this can be the difference can be quite heavy. For example, we can do just some simple multiplication for the true case and run another heavy computation graph for the false case. So, and this, if we could do that, then this will mean that this all of our operation will be very inefficient, because we'll finish computation for some values very fast, and then they will have to wait for others to get the results. So how to do that? How to write ifs in JAX? So essentially, you just need to reduce it to all the array manipulation. So in NumPy, there is a function called NumPy where it receives 3 values. The first value is the Boolean array. Second value is array which should be returned in case of true. And the third array is the array which should be returned in case of false. And so what happens here, assuming that x is array, first of all, we'll do the full computational execution for both true branch and false branch. As you can see here, before passing it to where, since it's NumPy, we need to compute x times 2 and x squared for the whole x. So we need to do both branches. We need to pre-compute both branches. And then we just have these 2 arrays, and we kind of mix them together based on the third one, based on Boolean one. So for every, like, this is equivalent to for loop. For every, if certain position of x at certain index is positive, then at the corresponding output we'll have this value, otherwise we'll have this value. So what do I have next? And this is another thing that you will need to use in homework. So remember, yes. So is there any questions about Vima? Okay, hopefully it's fine. Okay, now finally let's solve something real. For now, it's going to be just a very simple least squares problem. What I'm going to do, I'm going to create, I'm going to solve for x for some matrices A and B, just this simple optimization problem. It's convex, it's simple, and so on, and it's easy to solve it. And we are going to solve it with JAX. And obviously there are like convex optimization is a huge field. There are a lot of different algorithms in there. We are not going to use them, but instead we are going to use like something that corresponds to best practices that are there in JAX. So even though we are not going to use like the most efficient algorithm, we are going to use the algorithm that is widely used by JAX, and people usually implement that kind of algorithms. And this algorithm is, as you might guess, is just simple gradient descent. So, okay, so now we are using stuff that we already defined here. So we need to, let's initialize somehow matrix A and B. We just initialize them with a normal distribution. And as you remember, you should now be familiar with random number generation in JAX. we run it through the same process. We create random key, we split it into two subkeys. One we use to sample A, and then the second one we use to sample B. And of course, we split the key before that one more time. And this key, we can reuse it later again, which will happen in the next cell. And so basically A is a random normal distribution, where we also add some diagonal bias just to make the optimization easier for numerical models. And the same for B. So let's do like the best possible solution through like plain NumPy. This is not JAX NumPy. And surprise here is that you can take any, even when you're working with JAX arrays, you can take any NumPy function and put JAX arrays there, and it will be running properly. So yeah, so we computed the result. And now let's do the JAX stuff. So this is like the first real JAX, real-like JAX computation that you see here. And let's take a look what's going on here. So first of all, we start with our initial value for optimization. Again, like before, we split random number generator into two subkeys. And we sample the initial guess for X. So this function that is defined here will perform one optimization update given X and A and B. And as a result, it will return the updated X and criterion, which is like our optimization target that we minimize. In our case, it's normal of this residual, the L2 normal of this residual. So one thing that you might notice here is that I use JIT here in a little bit an unusual way. In particular, JIT is used as decorator here. So if you're familiar with Python decorators, you might know that this is equivalent to just update step equals to, so I'm going to write an equivalent formulation. This decorator is exactly equivalent to this. It just performs, it just passes this function as a variable to jax.jit. So let me bring it back to the decorator. And you obviously can combine many decorators in the same way. So let's see what happens inside of this function. As I said, it receives the previous optimization state, which is X. So we are going to optimize over X. Therefore, X is our optimization state. And A and B will be our like optimization inputs. The matrix and vector for which we are trying to find a solution. And so in here, we are going to define another function. And this is the point actually where we literally use closures explicitly. So I'm defining an objective, which is another function. It receives some X, and it uses A and B. And A and B, they are not changed. Therefore, it's a pure function. But A and B, they live in the closure of the objective. So this effectively, it's a very powerful and elegant trick. So in practice, you don't need to think about all the closures. Like it might sound hard initial steps when you just learn it, but once you get the idea, it becomes very easy and straightforward how to define these computations. So the idea is that we need to somehow define like what's the point of this closure? Why do we need to consider such a complicated thing? The idea is that we want to have a function with just one argument, right? So we want to have a function with one argument over which we will compute the derivative later. And so closures, they provide a very elegant way how to do that. You don't need to write any additional code for that. Everything will be done by Python behind the scenes. So you just define a function, you're like over which you will differentiate, and everything else will be just in the closure. So yes. And here we essentially define this, the L2 norm of their difference. So as you can see, like here, A is matrix n times m, x is vector size m, and B is a vector of size n. So the residual is this. It's like A times x minus B. And then we just square it, compute sum, and compute square root of that. And this is our objective to minimize. So what we are doing here, we are performing another transformation. This is new transformation, not really new, but technically new, that transforms a function. This transformation is very, very similar to the one that we consider, to the gradient. And we say that we don't want the gradient alone, but we want the output plus the gradient. And so we transform this function, and then we apply immediately this transform function to x. So, and as a result, we get the criterion that we minimize and the gradient of the criterion with respect to x. Why with respect to x? Again, because we pass x as input, and this function knows that I need to differentiate with whatever input is passed, with respect to whatever input is passed. I could have defined it in another way. For some reason, I could say, okay, my objective gets A as input, and pass A here, and in that case, it would have computed gradient with respect to A. But I need the gradient with respect to x, therefore I do it like this. And the last step is just the update of x. So again, I'm not updating anything global here. I'm just updating local variable called x, and I updated it like this. I take my previous guess, and I subtract the gradient because I'm minimizing the objective. I do gradient descent multiplied by some learning rate. And as a result, I return the updated state of optimization and the criterion. So please remember those words, updated state optimization and initial state optimization. We'll get back to them when we consider neural networks. So let's actually run the computation. Oops. I forgot to run this function. Okay, so as you can see, it's fast. And let's, so as a result, we got x, which is like the final result of optimization. The loss or objective function is very small. So let's see what we converge to. Oracle solution is this, and our solution is this. So they got pretty close, even though we had to do 10,000 steps, and it was, I'm sure it is slower than these fast and fancy optimizations. But the point of it is that when you train, as I told you, JAX can be used to train reinforcement learning agents. JAX can be used to train large language models. So the problem is that you cannot do anything like this for large language models or reinforcement learning agents. But pretty much the only way how to optimize modern AI models is exactly this. And so all of the optimization code that you'll see that is written in JAX will literally do this. So now we are going to do something even more real. But before I proceed, we have a little time, but I think that we'll be able to make it on time or like a few minutes later. But before I proceed, can you please let me know Please raise hands who know how neural network works and how they optimize, how they are trained. Okay, so I guess it's less than half. So that's not a problem. Basically, the reason I'm asking this question is because I know that you haven't been taught about this neural network thing. And since the assignment 3 assumes that you'll need to train some neural networks, you'll be given a proper theoretical introduction into neural networks on some lecture after today's one. But unfortunately, due to some logistics, we got some practical code that you have in tutorial actually before you are given neural network stuff. So I'm not going to, and this is actually the reason I included this least squares problem as an example of JAX, so that you should be more comfortable with these kind of problems. And I have an example of how it works for them. And so basically, the point is that I will try to give like a very brief and not in-depth introduction to neural networks. Please keep in mind that I'm not going to properly introduce you to neural networks. I'm just going to tell you what is needed for this in order to understand this tutorial. So first of all, the principle is very, very similar to what we consider here. We take some optimization problem, and we have two types of inputs. We have one input being the optimization state, which we call parameter, and another input being like input data, which we call being inputs to our optimization problem, which we call input data. And so you can think of a neural network as some black box thing, which is parameterized by some in general speaking, like vector of parameters. Can be set of matrices of many parameters, but we can always like consider them as one long vector. So we say that neural network is a black box operation that has two inputs. It has parameters and it has inputs. And the output of a neural network is the output for our problem. If you want to predict like, I don't know, cats and whether we have cats or dogs in images, we take images as input to neural network, parameters of neural network as input, and we can consider outputs of neural network being like binary flag, either 0 or 1, being either 0 or 1, where 0, for example, corresponds to cats, and 1, for example, corresponds to dogs. So the point of it is that the main mechanics of what's going to happen next, they are exactly the same as in this example, but we are going to consider a little bit more advanced libraries in JAX to make training neural networks easy for you as a user of neural networks. So basically, what I'm trying to lead to, it is normal and it is fine that if you don't understand fully what's going to happen next in the next slides, like what are the key principles, why are we doing certain things and not doing certain other things. So, and in one of the next lectures, you will be given proper introduction to functional approximation. And after that, you can review this part of the collab, and these things that happen next should make more sense to you. And ideally, it should be clear to you after the functional approximation introduction what is going on here. So let's solve something even more real. So we start with a data set, with a data that we train in neural network on. So this data set is simply, it's called MNIST, and I use library Keras for that. This library should be importable in Colab, so you can just run this code in Colab. And this is how this data set looks like. I just imported some library for plotting. This is a data set of handwritten digits. And this is a so-called classification data set. So there are 10 classes. Every digit is like, every example corresponds to a class between 0 and 10. So what we are going to do here, we're going to define a neural network to properly classify every input image. So here, first thing, we are going to import a few libraries that we are going to use. And there are 3 libraries. First is Flux. And Flux is a library within the JAX ecosystem that allows you to define neural networks. Second, the next one is Optax. Optax is another library that allows you to actually optimize any computation, including neural networks. So we could have done this least square example within Optax. It could be easy, but for transparency, we didn't do that. So here we define a neural net. And again, it doesn't matter exactly what is happening here. You should just perceive it as some black box computation with 2 inputs. One is here, it is X, it is in our case, image. And another one is parameters of neural network. So parameters are not passed directly here, but actually this is why I told you about this closure stuff. They actually live in closures of this function. So this allows you to not pass all these things explicitly to neural networks. So the definition of neural network is this. Neural network consists of layers and so-called nonlinearities. All layers is, so every layer is a linear operation, and every nonlinearity is, as the name suggests, is nonlinear operation. And the optimization parameters are defined only for linear layers, such as the convolution layer or fully connected layer. Again, you'll learn what are these things in one of the next lectures. Let me define a neural network. And the way how, and again, 95% of things that I'm talking about now, it was introduced in previous slides, and these are just different APIs of working with the same principles. So again, we create our model, our neural network, and we define like a synthetic input for the neural network. So to initialize neural network, we need to, similar to the previous least square example, we need to instantiate some random variables. So here, obviously, we need to create random state for that and split it because we'll use that random state later. So the initialization of neural network is done by Flux, and you just pass the random state in there and the input for neural network, because it actually passes this input through the whole neural network to initialize parameters. Yes, so it worked, and let's see what we got here. So first of all, what is the model? The model is our neural network, but it's not the actual like trained or untrained neural network. It is an object that defines that certain parameters, if we take them, which we initialize, they correspond to this computation. So this is like the object that corresponds to a certain computation. As I mentioned, like this black box computation. What is parameters? Parameters is, as you can see here, it could be very inconvenient to work it in this way because it's a dictionary of Python dictionaries with a lot of different arrays, and we initialize them in a certain way. This is actually some random numbers, random samples. So JAX actually provides very straightforward way to manipulate nested dicts of arrays, and you can do it in this way. There is a submodule in JAX called tree, and for example here I can add the number 100 to every single parameter I have. So now you see that they become biased. So the way it works is, remember, parameter is a dict of dictionary of dictionaries. And so if I want to apply the same operation for all of them, I can just define a function, and this function will perform like whatever I want. It takes like this array as input, and it performs some operation with that input. So basically, one thing about JAX is that it treats all Python objects as either arrays or PyTrees. And PyTrees are an example of PyTrees. We saw it in the previous slide. It was like it's, for example, like could be nested dict of dictionaries of arrays. And so JAX.tree.map is just a convenient way to work with PyTrees. And please note that this is another thing that will be used in homework, just because since homework 3 and homework 4, they assume that we work with neural networks. When we work with neural networks, we can work with their parameters. And so it will be useful to use this function in your home. Of course, you can do it manually, but this is just a recommended way. Unlike the previous one, for example, when I said that you need to do item assignment, of course, you can do it manually. You can like concatenate arrays, do some selection of indices, and do this manually. But this item assignment with this at notation is just a convenient way to do that. And again, jax.tree.map is another thing that is implemented for convenience. You can treat this way. You can treat parameters as just like vectors and treat them in a very mathematical way. And an example of this is here. So let's say I want to sum two parameters of two neural networks for some reason. Like we'll know probably why later. How to do this, I just want to do x plus y for every parameter we have. So I just do jax3map. I pass functions with 2 arguments, and I pass two pytrees as arguments to tree-map. And then what will happen? It recursively walks over trees, and it performs this operation that I pass here. It performs this operation for every array that it encounters during this walk over the tree. So summing the parameters of neural networks or PyTrees in general can be done in this way. And again, this is something that we highly advise you to use this function in your homework, but you are free to implement it yourself. If you want to write 3 times more lines of code, feel free to do that. So we did not train the network, but we can try to perform some classification to see what's going on. And as I told before, JAX allows us to define neural networks, where neural network is simply a function of parameters and inputs in a very mathematical way. So we literally do that. We say that we take our model, which defines our computational graph, and we apply it to the set of parameters that we have and input that we have. And so the output of this operation, since we are doing 10-way classification, is 10-dimensional vector. Because we in the end, we will want to determine a class by the maximal value in this vector, roughly speaking. So the optimization can be done really easily. here in JAX through the library called optax that we considered before. I just here create stochastic gradient descent object that will perform optimization via stochastic gradient descent algorithm. And behind the scenes, it is exactly the same as in the least square example that we consider here, except that learning rate is defined like this. So, and finally, we got into the actual optimization. So remember I told that neural networks, when we train them, we have some state of optimization. This is actually something very friendly to JAX as we saw in many examples previously. So Flax provides some standard way to define training state. Training state consists of three things. It is parameters for optimization. It is the function to perform some prediction on a neural network, and the optimizer. So we combine all these things together in a optimization state. And finally, we define training step as a function. So again, Ali, are we interrupt? Does anyone know if we are interrupt or no? Is there a class? Is there another class? Yeah. But don't we have a how it's called, office hours now? It's online. Okay. So yeah, we can I guess we can do the rest during office hours or in one of the next weeks. But yeah, we are actually almost done. There are like 3 more cells to run. And after that we can run training and you'll see what's there. So thanks everyone.